In this screencast for the 2023 fall cohort of Organic Chemistry 1, we'll look at exam 3, which is on physical organic chemistry. So the first 5 questions here, as we can see, the answers are just written in green by the numbers. So this screencast is probably going to be about an hour or so long. If you want, you could probably just fast forward through the different sections to see the key if you're just interested in the correct answer. But otherwise, I'm going to go through each question and give the logic and reasoning for that correct response. So questions 1 through 4, you're given these pKa values, and then you're given responses A, B, C, and D. And so you're asked to match the most acidic functional group to the pKa value. So for question 1, the pKa value is 5. And so when we're scanning across these functional groups, we see we have an acid for A, a ketone for B, an alkyne for C, and then a phenolic alcohol for D. pKa of 5 is going to be a carboxylic acid. For question 2, pKa of 10, that's going to be the phenolic OH. A pKa of 20 is going to be the ketone. And then the pKa of 25 is going to be the alkyne terminal H, as I just drew in there. So again, in the layering of concepts, when you're figuring out, the unique sets of hydrogen, you can classify those according to functional groups and then look on the pKa table, which is supplied in the back of the exam, to match those numbers. Question 5 is a mini structure elucidation question where you're given IR, mass spec, proton, and carbon. And the responses A, B, C, and D are basically molecular formulas. And so we can approach this a couple different ways. Let's just look at the data first, pick out the major functional groups, and then we can see what we need out of the molecular formulas, see if we can eliminate anything from that. So IR looks like it will have an OH functionality based on 35 to 3000, and as well as at the 1700, so that's our typical carbonyl. So if we look at just that and we consider what elements are there, we have a carbon, 2 oxygens, and then H, so CO2H thus far. And that can sort of remind us of carboxylic acid. And so within that, again, is the carbonyl, which is 1 degree of unsaturation. And so that's what we need to, when we're making our choice, make sure that there's actually a degree of unsaturation present in the molecular formula. So we looked at the IR, the mass spec. We see 2 masses, 90 is the parent and also the base peak at 100%, and then the N+1, which has a percent of 3 + 2, and you can if you recall that formula that we used in class, if you're looking at that M+1 signal, that tells you approximately the number of carbons. And so because it is 3, we can say, okay, there's approximately going to be 3 carbons. And so we look, A, B, and C all have 3. D has 4, but we don't want to eliminate anything just yet. Proton, let's just count the signals, 12.86, 4.7, 4.33, 1.38. So that gives 1H, gives 4 unique signals. And, you can see the multiplicities. They're broad singlet, quartet, doublet. So if something is a quartet, what is that telling us? That it has 3 neighbors. Something is a doublet. What is that telling us? It has 1 neighbor. And, that can give you an indication of what those functionalities are. So, you could have CH3, and then you could have CH. So those are some more fragments. And then we look at the C13 data. And we see there's 1, 2, 3 unique signals. And we already know the 183 is going to belong to the carbonyl. Then we see a 70.9 and a 23.8. So if we start piecing together what we know, say there is a carboxylic acid, and then we know there's 2 other carbons, so we'll just connect those. So 1, 2, and at this point, so that's a molecular formula of C3H6O2, and again the parent is 90. So let's see if that gets us to 90. So does this equal 90? So let's do the addition here. CHO, so 12, 1, 16 times 3 times 6 times 2, 36, 6, 32. So we do the addition here. 12 plus 2, 14. Carry the 1 up. 3, 3. So we get 74. So that's not 90. So what is the difference here? 90 minus 74. So that's going to get us our 10, so 6, and then so 16. So 16 is equal to oxygen. So we need to revise our formula to C3H6O3 to account for everything. And, at this point we can eliminate D. There's no odd mass, so we can eliminate that. There's no bromine based on the mass intensities of the M and the M+2. So it is C3H6O3, and then where's the other oxygen come from to meet the requirements? So the structure is that it's going to be 2-hydroxypropanoic acid. So the next set of questions regards to nomenclature, conformational analysis, structure elucidation. Again, we're layering all these concepts together now. So what is the name of this molecule? So let's put the highlighter on and trace what we think is the longest carbon chain from left to right. So we'll just start here. So there's 1, 2, 3, 4, 5. So it looks like it's a pentane derivative. And so if we're going on that, we can, immediately eliminate propane, butane. We're left with C and D, which are both pentanes. And then the difference between them is the locant numbers. 2, 3, 3 versus 3, 3, 4. And just sort of by intuition, you can look at C and say, well, if the nomenclature rules say they have to have the lowest possible numbers, C looks more correct than D does. But let's go ahead and write the numbers in so we prove that to ourselves. So if we start here at 1, 2, 3, 4, 5, well, we do see that it's 2,3,3 trimethylpentane. The other response D would be if you numbered the chain the other way. So 1, 2, 3, 4, 5. And again, the rule states that, when you add these numbers together, so we get 8, then you add these together, you get 10. You need to have the lowest number. The next question is asking us which Newman projection looks down the C3 to C2 bond. So that order is important. 3 looking down to 2. So you have to number it right to begin with. And then once you do that, you put your eyeball. So here's our little eyeball. And you're looking down 3 to 2. And so what that tells you is that the front carbon should have 2 methyl groups and an ethyl group. And we can see right away that A has methyl, but then it has isopropyl, so that's wrong. B has methyl hydrogen, so that's wrong. C, methyl ethyl, so we're onto something there. The back carbon should have 2 methyls and a hydrogen, so that looks correct. And then D has hydrogen, which is, that's actually looking down one of the methyl groups bonded to carbon 3, so that's also incorrect. Question 8, how much strain will the correct answer from response from question 7 experience? So that is, we're looking at 7C. And so 7C is staggered. And so really the only penalties that we know of in staggered will be the gauche interaction. So we count those. We have 1 there, 2, 3, 4. And so we take that, I think it was like 3.9 times 4, and then we'll end up with this value here, 15.2. So you can use some intuition and say, okay, that, A can't be right because you have methyl gauche. 28 seems a bit high, so you would be fighting between B and C, and you just do the calculation to figure out what's what. And question 9 says, what constitutional isomer of octane will experience the most rotational strain? So these you have to draw out. Anytime you see a name, you should draw it out. So 2,5-dimethylhexane. So we draw out 1, 2, 3, 4, 5, 6. 2, 5. 2,2,3,3 tetramethylbutane. So there's butane, there's 2,2,3,3. Wow, that one looks pretty congested. Heptane, 1, 2, 3, 4, 5, 6, 7, 2. Octane, 3, 4, 5, 6, 7, 8. So the linear isomer is probably going to have the least amount of rotational strain. When you start putting in the branching, so this one will have more, this one will have more, and then this one will have most, because now you're dealing with these eclipsing interactions. So eclipsing interactions increase as you branch off the main chain, and that's going to lead to more rotational strain. So B is going to be the correct answer for 9. Question 10 says, what data matches the structure of the amino acid valine shown. And so valine is this amino acid with the isopropyl side chain at the alpha position. So it says L, that's another stereochemical indicator. The naturally occurring amino acids have the L configuration. So let's just go ahead and convert this to the CYP, see if we can do some eliminations from there. So at the alpha carbon, we have 4 unique substituents. Let's draw on the hydrogen, it's going back. The nitrogen is 1. The carbon is 2 of the acid, and then the other carbon of the side chain is 3. So we're going clockwise, it's going to be S. We get rid of the R's. Now let's start looking at the data. So we have an acid, so we should have 35 to 3,000, so that's fine. We have the carbonyl, so something around 1,700 or so. So we can't eliminate any of these yet from B or C. They sort of make sense. The mass data looks to be the same, so we can't eliminate anything there. Again, 117, it's odd. It has 1 nitrogen, so it should be odd. Let's look at the proton and carbon data and just compare what's different. 12.39, 12.39, 8.9, 8.9, 4.29, 4.29, 2.08, 2.08, 0.96, 0.96, but oh, look here, this says quartet, that says doublet, so let's highlight that, that's a difference. This is quartet, that says doublet. Let's do some carbon counting. So 1, 2, 3, 4, 5, 1, 2, 3, 4. Whoop. So how many carbons do we have? Can we do an elimination there? So let's just highlight them. There's 1, 2, 3, 4 unique carbons. So that's going to eliminate that one, giving us D as the correct answer. So again, we could also eliminate based on this multiplicity here. That's another thing we could do an elimination of, the distractor. So let's move on to the next set of questions. In the next series of questions, we're dealing with stereochemistry of these 4 ADHD medications. And so we can see from 11, 12, 13, and 14, they're asking about the CIP designation, R or S. So if we look, just scanning from across, why don't we go ahead and start with A here. And so we have 2 stereo centers. So we'll mark those with the asterisks. Let's go ahead and determine the one with the nitrogen first. So if we're using, CNOF, increasing atomic number in terms of assigning priority. If nitrogen is greater than carbon, we can assign this to be 1. We have to be careful here because the H is coming out towards us. And then we run into this issue now with priority 2 because we have carbon and carbon. If we look what's bonded to each of those, we have carbon, H, and H. Here we have carbon, H, and carbon. So this has 2 carbons, so that's going to win. So let's go ahead and put the 2 there. So 2, 3, and we find that this is going counterclockwise, but because the configuration or the lowest priority is towards us, we have to reverse it from the S to the R. So let's go ahead and do that. So we'll assign that. Again, this one will be R. And so it says which one has RS. The next question says SS, then R. So this one has to be A because, again, there's two stereo centers. The question is asking R and S. So the other one has to be S. The next question is asking S and S. So that has to be C because that's the one that has two stereo centers. Then the next question, R, that has to be D. And then which one's shown as a racemate? So this one is the racemate because it's not indicating a wedge or a dash specifically. So that's the order of those from 11 to 14, but we can go ahead and just determine those other stereo centers. Let's just do D. So the H is towards us, oxygen is 1. Looks like this carbon is going to be 2. This carbon will be 3. And again, in determining between those two, we're looking at what's bonded to it. 2 has 3 carbons, 3 has 1 carbon, 2 hydrogens. So we're going counterclockwise, but the H is towards us. So we reverse the S to get the R. So for C, again, nitrogen is 1. We have hydrogen going back, 2 carbons. This has 3 hydrogens. This has a carbon, so that's 2. This is 3. So this one actually does end up being S because the H is back. The H is back here. Now this situation, we have carbon, carbon, carbon. This top one has multiple bonds to heteroatoms, so that's going to be 1. The right one has 3 hydrogens, so that's going to be 3. This other one has 2 hydrogens and a carbon, so 1, 2, 3. So that's going to end up being S. So that's the SS. So again, you can use a little bit of logic when you're going through these if the setup of the questions will allow for that. So 15, in consideration of the molecule from question 14, which is the racemate. And again, it's the racemate because it's not specifying the wedge or the dash, so that means it's a 1-to-1 R to S as drawn. So the question, however, is stating the S enantiomer has a specific rotation of plus 28. So the way I like to think about this, again, it's hard to memorize things, so it's easy if you spend some time just thinking about it. So at 0, that's your 1-to-1 mixture. And we'll just go to the right as positive. And, when you hit 28, that's the S enantiomer. Which means if you go negative to the left, 28, that must be R. So it says if a sample of this compound were analyzed by polarimetry and found to have a specific rotation of negative 22, so somewhere around here, 22.4, what is the composition of enantiomers? So this right away is telling you there must be more R in that sample because it's negative. So can we do any eliminations? So here S is greater, so that's gone. S is greater, that's gone. Now you have this choice here. R is greater in C and D. And we need to think about what the 22.4 is telling us versus what these compositions are telling us. So 22.4 over 28. If we take sort of 2, divide both of those by 2, we get 11 over 14, and then maybe just estimate either way. So what if it's, so we're going to do an approximation, 12 over 14. At that point, what do we have? 6/7. So it's pretty high, right? Even if you don't know like what those numbers are, it's almost closer to 100% than anything else. So what does this number tell you? What is basically the percent EE? So of the 75% of R, 25 of that is taken away by the S. So that's basically telling you that there's a 50% of the R. And so 50% of 28 would be, approximately -14. And so the value was -22. So just using some intuition, D has to be the correct answer. But can we sort of reason that out as well? This using the same thing, 90 minus 10, that's giving you 80. And so I would say the 11 over 14 is closer to 80 than it is to 50. So just using some reasoning, this seems like a more logical composition. So again, calculators aren't allowed on the exam, but you should be able to sort of reason, based on some first principles. So let's move on to the next run of questions. Here we're at 16 to 20, using nomenclature, conformational analysis, and SIP designations. And so the question is giving you the name of the compound. So 2-isopropyl, 5-methyl cyclohexane 1-all. So it's giving you the positions of the substituents on the cyclohexane ring. And it's giving you this clue here as well. Natural menthol has the levorotatory rotation. So levo is negative. And the question is asking you which one of the chair conformations is the lowest energy or most stable. So with chair substituents, you want to put them equatorial as much as you can. And then really what you're looking for is that, as well as having the correct relative 1-to-5 relationships amongst those substituents. We look at A. There's alcohol at 1, isopropyl 2, 3, 4, 5. So that has the correct relative relationship, but these are all axial, and the question's asking you most stable. So that one, we can eliminate. So what about B? So 1, 2, 4, 5. Oh, that looks pretty good. Is that right? Let's go ahead and look at the other ones. We don't want to eliminate anything just yet. 1, 2, 3. Uh-oh, the isopropyl's at 3, 4, 5, 6. So this has incorrect relationship amongst the substituents. What about D? 1, 2, 3, 4, 5. Yep, that looks pretty good. So B and D are now what we're determining between. And then if we look at them, they are mirror images of one another. So they're enantiomers. So one of them is the levo, one of them is the dextrorotatory, which is the next question. And so you have to convert that flat molecule into the chair, and when you do that, you'll see that D is the correct answer for the levo, and then the next question, B is the correct for the dextrorotatory. So moving on to question 18, the magnitude of the specific rotation of menthol is 50. So let's just write that there. This is plus 50, this is minus 50. If 4 moles of the natural enantiomer, so 4 moles of this were mixed with 1 mole of this, what would the resultant specific rotation be? So it's got to be negative. So we can eliminate that. So it's basically and it has to be closer, the percentage is closer to 50, right? So it can't be 10. So we need to look at the equation that's given to you, and we would basically say, okay, we have 4 moles. We're going to subtract out 1, and then we're going to do the addition for plus 1. So that's going to give us 3 over 5. And so that's what, 60%. And so what is 60% of 50? So if you take 50 times 0.6, that's, when you multiply that out, you're going to get basically 30. So 30 is going to be the correct answer. 45 is a bit too high in terms of dealing with this ratio. So again, you can approximate if you have, if it was 0.5, so half of 50 is 25. So that's closer to 30 than it is to 45. And again, that's sort of the logic you want to use in helping you eliminate some answers that are further away from what you're looking at. So 19 plus isomenthol is 1 diastereomer of naturally occurring menthol. Which one is 1s? It has the 1s 2R 5R configuration. So which one is isomenthol? So the easiest thing to do is just go back to menthol itself. Determine the configurations. So position 1, oxygen is 1. H is going back, so that's the lowest priority. Now you have carbon. Carbon, this has 2 hydrogens and 1 carbon. This has 2 carbons, so that's second priority. This is third. So you're going clockwise, so position 1 is R. So can we eliminate anything based off that? So we need 1s. So if we sort of manipulate the answers A, B, C, and D through, say, flips or rotations, we want to see if we can eliminate any of those based on this the 1R being the wedge. So that means the 1S must be the dash. So B we see is oriented the same. That's the dash, that has to be S. C is oriented the same, it's the wedge, that has to be R, so we can eliminate that. Now, if we look at D, D is a mirror image. And so what that's going to mean is that alcohol, even though it's a wedge, it's not in the same orientation. See how it's the mirror image? So that means that must be S, so that's in the running. If we look at A now, if you do a rotation of A, so 180 degree rotation, you'll find that it's going to flip that alcohol towards you, and that would then be R. So we could eliminate A then as well. So we're really between B and D at this point. So what we can do is move on to the next stereo center 2, see if we can do any sort of eliminations like that. So let's start with 2 is the isopropyl group. And so here we have H. Now, in this case, we have carbon, carbon, carbon. So what wins? The one bearing the alcohol, that will be 1. Then between the two, you have 1 carbon, 2 hydrogens, 1 hydrogen, 2 carbons. So that's 2. Then this is 3. So this you're going clockwise, which would be R, but the group is toward you, so that would be S. So that's 2S. And so right there we can say, okay, well, it has to be R. So we can eliminate that. But if we go back and just verify for D, that D is the correct response, we can do the same thing. This is towards you. So 1, 2, 3. This is going counterclockwise. It's toward you. So instead of S, that's going to be R. So 1S, 2R. And then, you do the same thing over here. H is towards you. They're all carbons. This one has 3 hydrogens. That's going to be the lowest priority. You go out to these 2 here. They're sort of the same, but then you go back down, and now you're hitting this carbon with the oxygen, so that will be 1. This will be 2. So you're going 1, 2, 3 counterclockwise, but you reverse it to the R. So that's how we get D is the correct response there. So again, you can move back and forth between these responses to help eliminate derailers as you solve these problems. So this question is asking you, in consideration of the structure from question 19, in its most stable chair conformation, what is the dihedral angle between the hydrogens on carbons 1 and 2? So let's go ahead and start drawing some chairs here. So if I call this carbon 1, the alcohol is up. That means that hydrogen is down. So next is carbon 2. The isopropyl group must be down. So that means that hydrogen is up. Go around the ring. 3, 4, 5. That H is equatorial, so the methyl group is axial. This would be the most stable compound, though, or conformation, because you have the large group equatorial. alcohol equatorial, the methyl group's going to have to stay axial. So what we're looking at is this dihedral angle here. And so they're anti, and so they're going to be 180 degrees. So in our next run of questions, we're given pseudoephedrine and the IUPAC name 2-methylamino 1-phenyl propane 1-all. So that helps us with solving these as well, because we have these 1 and 2. So the 1 is bearing the alcohol, the 2 is bearing the amine in terms of the chain. And so it says of the zigzag drawings here, which one is 1R, 2R? So let's just start with A. So this is, again, the carbon bearing the alcohol is position 1. So we need that to be the R. So oxygen's going to get 1, hydrogen's going back. So this carbon, this one has nitrogen, so that's 2. This is going to be 3, so we're going clockwise. So that is the 1R. Let's do some erasing. Now we'll go to carbon 2. So we have this, hydrogen's going back, nitrogen's 1, carbon, 3 hydrogens, oxygen, that's 2, 3, we're going clockwise, so that is 2R. So A is the winner here. And then because the questions below relate to this, and we see already that the molecule has 2 stereocenters. So we have 2 to the 2. That equals 4 total stereoisomers. We said this was R. That's R. So this is S. That's R. This is SS. And this is RS. And so that's going to help us with these next ones, because we're looking at now a Newman projection and then a Fisher projection. So this one's asking us 1s, 2r. And so 1s, this one here is 1s, 2r. So we need to find this one as the Newman projection. And so what it looks like is that we, in all of these, we're looking down carbon 2 to carbon 1. So all of these are C2 to C1 in the Newman projection, which means your I is here. So methyl on top, nitrogen to the left, hydrogen to the right. So methyl on top, nitrogen is to the right, we need it to the left. Methyl on top, nitrogen to the right, hydrogen, nitrogen to the left. So this is a possibility here, as is D. And now the amine is on the left. The alcohol should be opposite. So these are the same, so it can't be that. So to the left, to the right, it's got to be D. And now 23, we want 1R2S. So 1R2S, we go back to 21. 1R2S needs to be that one. They're all formatted the same. So this is a Fisher. Fisher projection. And again, the Fisher projection, we're looking down the backbone. It's showing the phenyl ring at the bottom, the methyl group at the top. And so, we just need to get our vantage point. So for this one, essentially what we're going to need to do in the zigzag conformation is we need to do a rotation about this bond where this methyl group becomes eclipsing now with the benzene ring. So we need those eclipsing. And then it looks like we're putting our eye right here and looking down that bond. So if we do that and we put the phenyl group on the bottom, we put our eye here, the hydroxyl group should be on the right. So it's left, this is right, that's a possibility, that's left, right. So we're between B and D. Now when we do that rotation, that amine group in the zigzag, it's opposite the hydroxyl, but when we do the rotation, the amine group should be on the same side as the hydroxyl. And so that's going to be B here, and we see in D it's opposite, so that can't be right. And so what I mean by the rotation, the methyl group is down, and now the amine group is on the same side, and again your eye is there, and you're looking at that bond. So this is going to be the bottom. This is going to be the top. Then those substituents end up being on the right side of the Newman projection. So what base would be strong enough to deprotonate the most acidic functional group in pseudoephedrine irreversibly? So this is not a base. Sodium hydroxide, sodium hydride, potassium acetate. Draw out their conjugate acids, determine the pKa's, so 14, 40, and 5. So 40 is going to be the winner. Sodium hydride will irreversibly deprotonate the alcohol. So again, what you're dealing with is OH plus some base going to RO minus plus the conjugate acid. So we know that the alcohol is about 16. Then you're comparing those numbers here. So 14, 40, and 5, and you want it to go to the weakest acid-base pair. 16 and 14 are too close. 16 and 5, you're going the wrong way. You're going more acidic rather than less acidic. The last one in this set, if pseudoephedrine was treated with HCl, what's the approximate pK of the conjugate acid that's formed? So what are you doing? You're taking the secondary amine, treating it with HCl. You're generating the salt. And that's going to have a pK of 10 as you look up on the chart that's given to you in the back of the exam. The last run of questions is the structure elucidation. So you're given the IR, mass spec, and carbon, IR, mass spec, proton, and carbon data. Again, based on the way this software is, I have to go through these stepwise. I can't flip back and forth, so I'm going to give some clues about things prior to talking about them from mass spec and proton before we even get to it. So in the IR, we draw a line down here, so 15, 16, 17. That tells us there's a carbonyl. So we have CO, 1 degree of unsaturation in our fragments. Then we look over here, there's nothing in region 2, so no alkyne, no nitrile. Azide is also a triple bond, so none of those. When we look in region 1, when we're drawing sort of straight down here to here, we're 3,000, 1, 2, 3, 4, so 5. Even though it's not the prettiest, this is indicative of the OH. It doesn't exactly resemble what you're used to seeing in the textbook. But that is a heteroatom H stretch, and it looks more like the OH than it does an NH. But again, we'll confirm the presence of oxygen versus nitrogen in the mass spec a little bit later on. So we have OH, so that's 0 degrees of unsaturation. So total from the IR, we have CO2H, and hey, that we know that's the minimum requirement for a carboxylic acid. So this could be a fragment. Just go ahead and propose it now. So here's the mass spectrum. Again, we're mass to charge. Z is typically 1, so we're dealing with the mass. And then we're dealing with, the intensities over here. So when we go all the way to the highest mass, so we see this cluster in this region here. So this cluster, we have a mass of 156, so that's going to be the parent. And then you have this other mass at 158. So that is M plus 2. And so if we draw a line over, so there's 100%. And then we look at this M plus 2 at 158, and we draw a line back over this way from there. You're hitting about 30%. And so what is that telling you at this M plus 2? You have about a 3 to 1 ratio, and that's telling you there's probably a chlorine. It's not bromine because that M to M plus 2 is not 1 to 1. It's about 3 to 1. Because this is even, there's no nitrogen, or no odd number of nitrogen. Could be an even number of nitrogen, but we're just going to assume there's no nitrogens. So in terms of the heteroatoms, just using that data thus far, we have the CO2H, the Cl, and again, if the chlorine is giving 35 mass units of the 156, the CO2H is giving 12 plus 32 plus 1, so that gets you 45 mass units. So those two together are giving you so 80 atomic mass units of that 156. So that's useful as well. We can also again do the normal thing. If we take 156 and we're just considering the heteroatoms now, so minus 32 from the oxygen, so that gets us 4, 2, 1. And we back off 35 from the chlorine. So that's going to give us 89. And so the 89 is telling us what we're assuming is the remaining C plus H So if we take, 89 divide by 12, that's going to give us an indicator of the maximum number of carbons. And so if you take, 12 times 8, just do in your head real quick, that's at least 80. And then you add the other so 12 times 8, what do we need, 16, so that's like 96. So it can't be 8, so it's got to be 7. So what is that? 12 times 7, that's 70, plus 14. So 7, because 12 times 7 is 84. And then is that reasonable? So 89 minus 84 due to the C, that would give you 5H. And so what do we know? C7H5 ClO2. If we convert that, C7, oxygen does nothing, chlorine will add 1, H6. For 7 carbons, that should be 16, H16. We would get H10, and a degree of unsaturation is H2, so that gives us 5 degrees of unsaturation. So that's reasonable. Whenever you're above 5, or whenever you're approaching this larger number, a good fragment to keep in mind is a benzene ring, because that's automatically 4. So 4 degrees of unsaturation. We have a chlorine. We have a carboxylic acid. And so that's starting to make some sense there. 6, 7 carbons, a disubstituted benzene. It's going to give you 5 hydrogens. So let's go to the next piece of data and start piecing things together. Here's the proton data. The first thing we want to do is just count the unique sets. This is 1, 2, 3, 4. And so we're not counting it, confusing ourselves. This is solvent. So we do not count that. So we have 4 unique sets shown. From the prior data, we have 5 total hydrogens though. But if you look at the region in which these are in, so 7.4 to 8.1, we know that this is the aromatic region. So that means the carbons are sp2 hybridized. If they're on a benzene ring, they can only have 1 H. So that means the integrations, the ratios in the sets here would be 1 to 1 to 1 to 1. But we also said from before, there's most likely a carboxylic acid. So that would be the 5th H. So it looks like we're dealing with this situation of 4 aromatic hydrogens. The 5th one being the acid. And so we have a benzene ring, based on where we're placing these H's here. Let's move on to the carbon data. We'll confirm that. And so what we can gather from this is solvent. So we do not count that. These peaks are jammed together, but what you can do here is count these. So 1, 2, 3, 4, 5, 6, 7. This has to be the carbonyl. You have, therefore, 6 remaining, so it has to be a benzene ring. Now the question is, what is the substitution pattern of the benzene ring? Because you have the chlorine substituent and you have the acid substituent. So you have 2 substituents. What are the scenarios? That's one scenario. It's 2 scenario. This is the 3rd scenario. And what are you really doing? You're saying, that's the 5th H. So you have 4 H's on the ring. We saw 4 unique signals. So can we count? Can we use that to eliminate? So in the 1-2 relationship, this would be 1, 2, 3, 4. So that's a possibility. In the 1-3, you have 1, 2, 3, 4. That's a possibility. In this, you have 1 and 2. So let me just use different colors here. So those indicate the unique sets there. So again, we're between now these 2. And so how would we differentiate them? Again, if we recall, the proton data had something that looked like a singlet. And so this is going to be the final answer. Is this 3 chlorobenzoic acid. Really, because of the singlet is the giveaway. If you do the multiplicities for everything else, you have a doublet, a triplet, a doublet, a doublet, a triplet, a triplet, a doublet. So when you're doing that 4 to 1 to 1 to 1 to 1, what you see in that spectrum is a singlet, a doublet, and a triplet. So the 1-2 relationship shown here would have 2 doublets and 2 triplets. So the DEPT NMR confirms what we already know. Again, these are all up signals. They're in the aromatic region, so they have to be CH. These ones that do not show are the ones that are bonded to the ring substituents. Would be this carbon and that carbon. And then again, this is the sp2 hybridized carbonyl carbon. And then finally answering the questions for this. Based on the IR signatures, we know it's an acid, so the pK is 5. What is the total heteroatom contribution? So again, we had 32 plus 35. That's going to give us 7, 6, 67. So it's going to be that. We sort of did that calculation, but we had included the carbon, but now we take that, that 80 that we calculated, we strip out the carbon and the H, so we get to 67. Degrees of unsaturation is 5. The carbons have sp2 hybridization. And then the last question again, the final structure is the 3-chlorobenzoic acid. So again, that'll wrap up our exam 3 on physical organic chemistry review screencast for the fall 2023 cohort.